Welcome back to Talk Tensors. Today we're doing a deep dive into a really interesting paper.
Yeah, this one's called ASMA-Tune, Unlocking LLM's Assembly Code Comprehension via Structural Semantic Instruction Tuning.
Quite a mouthful, but basically it's tackling a core problem in ML and cybersecurity too, getting AI to really understand low-level assembly code.
Exactly. And assembly, well, it's the fundamental language computers actually run on. Super important for reverse engineering, finding vulnerabilities, even optimizing software.
Right, but it's not like Python or Java, is it? It's dense.
Oh, incredibly dense. And it doesn't have that clear structure you see in high-level languages. That makes it really, really tough for automated analysis.
So this paper introduces ASMA-Tune. It's a new framework aiming to bridge that gap, right, between assembly code and how LLMs understand language.
That's the goal.
Okay, so our mission today is to unpack how ASMA-Tune actually works, why it's a potentially big deal, and maybe what doors it could open up down the line.
Let's get into it.
So first off, can you give us the quick summary of ASMA-Tune? What is it at its core?
Okay, so ASMA-Tune is what they call an end-to-end structural semantic instruction tuning framework.
Right, breaking that down.
It basically tries to combine the best of both worlds. It uses encoder architectures, models that are good at understanding the structure of assembly code, and fuses them with decoder-based LLMs, which are great at, natural language tasks.
How does it fuse them? That sounds like the tricky part.
It is. They use something called projector modules. Think of them as translators, maybe. They align the way the assembly encoder represents the code with the LLM's understanding of language and concepts.
Okay, so it's aligning those two different worlds.
Precisely. The aim is twofold. Make the AI better at understanding the assembly itself, and make it better at following instructions about the assembly code in natural language.
And they found it works better than what we had before.
Yeah, the experimental results they show suggest it outperformed the existing benchmarks, quite significantly in some cases.
Before we dive deeper into how ASMA-Tune works, maybe we should talk about why this is so hard in the first place. What makes assembly code such a challenge for AI?
Well, we touched on it, but it's worth repeating. The information density is low. You get these tiny instructions.
Like MOV, ADD, JMP, that kind of thing.
Exactly. Very cryptic on their own.
Yeah.
And there's no explicit syntax like if this, then that loops, or clearly defined functions like you see in higher languages. It's all implicit in the instruction flow.
So piecing together the big picture is tough.
Very tough. And bridging that gap to natural language, say, asking an AI, explain this vulnerability based on the assembly, or turn this back into C code. That's been the major roadblock.
The paper mentions previous approaches, masked language modeling, MLM, like BERT and similar models.
Wow.
What was their deal with assembly?
Right. So MLM-based methods, things like CodeArt, CLAP, ASMA-Tune, they were actually pretty good at learning the semantics within assembly. They could figure out that certain instructions often go together or have similar meanings.
Okay, so they understood the assembly's internal logic, sort of?
Yeah, you could say that. They were good encoder-centric models.
Oh.
But the big limitation, they weren't really built for generating natural language. They could learn representations, but they couldn't easily explain the code or answer questions about it in English.
Got it. Understanding, but not explaining.
Pretty much.
So then what about the other way around? Using the big decoder LLMs like the GPT series or Llama, they're amazing with source code, right? Why do they apparently struggle with assembly?
That's a really key point. You'd think they'd handle it, but assembly's nature trips them up. The meaning is much sparser, and it's tied very closely to the hardware.
Unlike, say, Python, which runs more abstractly.
Exactly. Standard LLMs are trained on vast amounts of text and higher-level code. They often just miss the subtle, hardware-specific nuances in assembly. The paper argues that just treating assembly like any other text sequence doesn't work. It fails to recognize its fundamental hardware-centric nature.
So even recent attempts to fine-tune LLM specifically for this, like LLM compiler or LLM for decompile, they ran into problems.
Yeah, they still face this basic misalignment. The way LLMs learn is very language-focused, and that doesn't quite mesh with the low-level reality of assembly.
Okay, so this really sets the stage for ASMA-Tune. How does it specifically address these limitations? What are the key pieces?
All right, so ASMA-Tune has three main components working together. First, the assembly code encoder module.
The part that understands the assembly structure.
Right. It's built to capture those hardware-level patterns, the specific instructions used, the control flow, like jumps and calls, names of external functions it talks to. They actually use an existing architecture called CLAPASM for this.
Okay, component one, assembly expert.
Component two, The projector module, and this is maybe the most crucial bit, it acts as the bridge.
The translator we mentioned.
Exactly.
Yeah.
It takes the numerical outputs, the embeddings, from the assembly encoder and maps them into the same kind of meaning space the LLM uses for language. Interestingly, they borrowed an initialization technique from LLVA.
LLVA, that's the vision language model, right?
Yeah. It aligns images and text. They adapted that idea to align assembly and text.
Clever. And the third component?
It's the LLM module itself. It keeps all its powerful natural language processing abilities. In their experiments, they used VICUNA V1.5 13B as the base LLM.
So you have the assembly expert, the LLM expert, and the translator connecting them.
That's a good way to put it.
Now, getting this complex system to work must require some pretty specific training data. How did they build the data sets for ASMA-Tune?
Oh, absolutely. The dataset creation was a major effort. They did two main things. First, they took standard source code collections, the Juliet test suite, binary crop 3M.
Stuff used for security testing and research.
Exactly. They compiled that source code into assembly using the GCC compiler. And here's a neat trick. They used randomized optimization levels during compilation.
Why random?
To create variety. The same source code compiled with different optimizations looks quite different at the assembly level. This makes the model learn more robust general features, not just memorizing one specific compiler's output.
Smart. Okay, so that gives them lots of assembly. What else?
The second part was generating the language side. They used GPT-4 Turbo, a very capable LLM, to create conversations and descriptions about the assembly code they generated.
So using AI to create training data for another AI.
Precisely. They created two data sets this way, D1 and D2. D1 had simpler, basic descriptions of what the assembly did.
Like a high-level summary.
Yeah. And D2 was much richer. It included detailed explanations, back and forth conversations about the code, and even complex reasoning tasks related to the assembly.
Wow, okay, that sounds comprehensive. How did they use these data sets in the actual training? What were the steps?
It was a two-stage process. First, ASMA-Tune pre-training.
Yeah.
Here they focused on training just the projector module.
The translator.
Right, they used that simpler D1 dataset. The goal was to teach the projector how to map the assembly encoder's output to those basic textual descriptions. They used something called an autoregressive loss.
Which means?
Think of it like teaching the model to predict the next word in the description, given the assembly code. It forces the projector to find meaningful connections between the assembly features and language elements.
Okay, so stage 1 aligns the basics. What's stage 2?
Stage 2 is ASMA-Tune end-to-end fine-tuning. Now they train both the projector and the main LLM module together, using the more complex D2 dataset.
The one with detailed descriptions, conversations, reasoning?
Exactly. Still using that autoregressive, predict the next word approach. But now the goal is to deepen the mutual understanding between assembly and language, to make the whole system capable of handling more complex instructions and reasoning.
Got it. Pre-train the translator, then fine-tune the whole system for complex tasks.
That's the essence of it.
And this led to the strong results you mentioned earlier.
Yeah.
Let's talk about those. They looked at binary code similarity detection, BCSD. Why is that task so important?
BCSD is huge in security and software analysis. It's about figuring out if two different chunks of compiled code basically do the same thing, even if they look different on the surface.
Like finding if a known vulnerability from one program exists in another slightly different one.
Exactly that. Or tracking malware families, or finding code plagiarism. It's fundamental. And ASMA-Tune, specifically their 13 billion parameter version, ASMA-Tune 13B, did really well here.
How well?
They tested it on 7 standard BCSD benchmarks, Benoodles, Coroutils, OpenSSL, common stuff, and it outperformed other state-of-the-art models, including big names like GPT-4 Turbo, Codalama Instruct, DeepSeek Coder, across key metrics like recall at 1 and MRR.
Impressive. Any specific areas where it really shone?
Yeah, they noted it showed significant improvement, particularly in scenarios with complex control flow in the assembly. That's often a weak spot for models that just treat code like text.
That makes sense, given its structure-aware encoder. What about the other benchmark, ASMA-Bench? That was one they created themselves, right?
Yes, ASMA-Bench was designed specifically to test the instruction following aspect. Can the model understand and act on natural language instructions about assembly?
Okay, so less about similarity, more about interaction.
Right. It has 2 parts. One based on that binary crop 3M dataset, and another using in the wild samples real-world assembly from things like crypto libraries, even malware.
And how did ASMA-Tune do on its own test?
Again, State-of-the-art performance. It excelled at generating conversations, detailed descriptions, and complex reasoning about the assembly code. They found it even matched or sometimes beat GPT-4 Turbo on these tasks.
Even beating GPT-4 Turbo on tasks about assembly, that's quite a claim.
It highlights how specialized training really pays off for this domain. General-purpose models are amazing, but for deeply understanding something like assembly, this focused approach seems very effective.
They also did ablation studies, right? Taking bits away to see what matters most.
Yeah, standard practice in ML research, but always insightful. They basically confirmed that all the pieces were important.
Like the different types of generated data.
Yeah. Removing the conversation data or the detailed descriptions or the reasoning examples, each one caused a performance drop. So that rich mix in the D2 dataset was key.
What about the model components?
Same story. The specialized assembly encoder, crucial. Performance dropped significantly without it. The pre-training stage for the projector, also critical. Skipping that initial alignment step really hurt the model's final abilities.
So no shortcuts, basically.
It seems that way.
Yeah.
And they also confirmed that size helped the 13B model was better than a smaller 7B version.
Okay, let's zoom out a bit. How does ASMA-Tune fit into the history of trying to understand assembly code? What came before?
Well, for decades, it was mostly manual analysis by highly skilled humans, maybe aided by static analysis tools looking for patterns or dynamic analysis tools watching the code run.
Painstaking work.
Incredibly so. Then came early machine learning, often focused on handcrafting features from assembly instructions. Deep learning then brought models like the MLM ones we discussed, which could learn embeddings automatically.
And then the LLM revolution happened.
Right. LLM showed amazing results on natural language, then on high-level code. So the natural next question was, can we adapt this power for the low-level world of assembly?
And ASMA-Tune in an answer to that question.
It's a significant step. It feels like an evolution, drawing ideas from multimodal learning, connecting different types of data like images and text, and applying that philosophy to connect the very different worlds of low-level assembly structure and high-level natural language.
So thinking about the real-world impact, what could this actually enable? If this technology matures, what changes?
The potential is pretty broad. For cybersecurity folks, think enhanced reverse engineering tools, making it faster and easier to understand malware or analyze closed source software.
That alone is huge.
Definitely. And better vulnerability detection. An AI that can reason about low-level execution might spot flaws missed by current scanners.
What about outside security?
Software optimization. Getting a deeper understanding of hardware-level performance bottlenecks could lead to more efficient code. And maybe, down the line, better automated decompilation or even translating between assembly for different processors, though this paper focused on by 8664.
Lots of potential there. Okay, this brings us to our novel notions segment. Thinking beyond the paper, what are some new research ideas ASMA-Tune could spark?
Okay, here's one thought. What about applying ASMA-Tune to obfuscated assembly code?
Code that's deliberately scrambled to make it hard to understand, like in malware or software protection.
Exactly. Since ASMA-Tune has that structural understanding component, maybe it's more resilient to surface-level obfuscation than models just looking at the text sequence.
Interesting. So it might see through the disguise.
Potentially. You try creating data sets.
Right.
Here's obfuscated code. Here's a description of what it actually does underneath. Then fine-tune ASMA-Tune to make that connection, if that worked.
Wow.
Huge implications for analyzing protected software or advanced malware.
That could be a game changer for reverse engineers. Okay, what's another avenue?
Another idea is integrating dynamic analysis information. Right now, ASMA-Tune mostly looks at the static code, the instructions as written.
But code does things when it runs. Values change, paths are taken.
Precisely. What if you could feed information about the code's runtime behavior execution traces, register values over time into the ASMA-Tune framework?
So combining the static view with a dynamic view.
Yeah. Could that give it an even deeper understanding? Especially for tasks like explaining why a vulnerability occurs, which often depends on the program's state during execution.
How would you even feed that dynamic info in?
That's the research challenge. You'd need new ways to encode that runtime data and fuse it effectively with the static assembly embeddings inside the model. But if you could crack that, you might get a much more holistic, accurate picture of what the assembly is truly doing.
Combining static structure with runtime behavior, that sounds powerful. Those really fascinating directions.
They build directly on the core ideas of ASMA-Tune.
Absolutely. So wrapping up, SMA-Tune definitely looks like a really promising step forward for getting LLMs to grips with assembly code.
Yeah, that combination of assembly-specific encoders and the power of LLMs seems like a very smart approach for this tough domain.
And the work they did creating the ASMA-Bench dataset is a contribution in itself, helping future research.
No doubt. Good benchmarks are essential.
Well, if this has piqued your interest, we strongly encourage you to check out the full paper. As always, the link is in the description.
Definitely worth a read if you're into low-level code or AI for security.
And we'd love to hear your thoughts. What do you see as the future of AI and understanding low-level code? Let us know. Thanks for tuning into this deep dive on top tensors.